Hello everyone, we're going to be doing our chapter 4 review for our test tomorrow. So we're going to start with section 4.1 and we'll go through sections to 4.4. So starting with section 4.1, we learned about exponential functions, which are written as, and we see our function of x, or f of x, is equal to the base, which is highlighted in red, so this will be any positive constant number. And then we have our exponent, which is in blue. So for example, just like examples of exponential functions would be y is equal to 10 to the x power, f of x is equal to 5.6 to the 2x power, g is equal to 7/3 to the 0.5 power. So those are just some examples. Whenever we see them written, they're always written as the base with the exponent. Usually the exponent is what contains the variable. Then we see that exponential functions can model exponential growth or exponential decay. So exponential growth will be when something starts growing and then it starts growing at a much more rapid pace. And so we get this kind of upturned curve, so exponential growth. And then when we have exponential decay, it's very similar in the sense that you start very quickly decreasing, and then you start to decrease less and less and less as you're getting closer to zero, but you see it kind of slopes downwards. So whenever we have an exponent that's negative, or if the base a is between 0 and 1, then we get exponential decay. So this is one or the other. We see when the exponent is negative, or if the base a is between 0 and 1. This is how we end up getting exponential decay. Then, when an exponent is positive, and the base of a is a greater than 1, then we get exponential growth. So for exponential growth, we have when the exponent is positive and when the base is greater than 1. And that's how we get exponential growth. And then included here are just examples of what our exponential decay and our exponential growth graphs will end up looking like. Then we went on to talk about the number e, which e is equal to about 2.718, and it is an irrational number and the most useful exponential function. So we'll see it written a lot of times as f of x is equal to e to the x power. And so that would be an exponential function of e. And like we said, e is an irrational number. We round it to about 2.718, but the number e technically goes on and on forever, just like pi does. All right, going into our first example, we want to describe the shape, so basically whether it's going to grow or decay, of the graphs of these exponential functions without graphing. So without graphing these functions, we want to see whether it will be growing or decaying. So if we consider our first part here, part A, we have f of x is equal to 6 to the power of 1.9 times x. So what we see here is that we have a positive base that is greater than 1, and we have a positive exponent. This is the case that if we think about if x is positive itself. So when we say positive or negative exponent, we mean is there a negative sign in front of our exponent? So in this case, we have a positive base and a positive exponent. So we would say that this function will grow exponentially. All right, so now we can look at our problem B. We have f of x is equal to 3/2 greater than 1 to the power of negative 3x. So we see that our base is greater than 1. It's not between 0 and 1, even though we do see a fraction. But our exponent has a negative sign in front of it. And because we have this, we know that this function will decay exponentially. So if you ever come across a problem like this and maybe you are confused or need another way to kind of figure out if it grows exponentially or decays, then by all means find a few values of x and then calculate f of x or y in any case, and then you'll have a good kind of point of reference if you have definitely a few points there to see if it's going to be growing or decaying. So now that we decided which functions are growing and which functions are decaying, we want to find the first two coordinates, and we want to round to 1 decimal point, or our 10th decimal place. So with our first function here, we have that x is going to be 0 and 1. And then we have our equation y is equal to, or f of x is equal to 6 to the power of 1.9 times x. So if we plug in 0 for x, we're going to get 6 to the 1.9 power times 0, and that's going to give us 6 to the power of 0. We know that anything to the power of 0 is just going to be 1. So you know that that is just going to be 1. Now we can calculate for when we have x equals to 1. So in this case, we have 6 to the power of 1.9 times 1. And when you calculate this value, you should end up getting 30.1. Now we can move on to our second part here. So we have x, once again, we have 0 and 1, and then we have y, or f of x, is equal to 3/2 to the power of negative 3x. And once again, we're going to try 0 and 1. So we know that when we plug in 0, we'll get 3/2 to the negative 3 times 0 power. So we know that anything times 0 is 0. So this is technically y is equal to 3/2 to the 0 power. We know anything raised to the 0 power is just going to equal 1. So we have 1 there as well. Now we can calculate for x equaling to 1. So we can have y is equal to 3/2 to the negative 3 power times 1. This is essentially going to be y is equal to 3/2 to the negative 3rd power. And when we calculate this value, we end up getting about 0.3. So we definitely see with our first function here, it is definitely going to be an exponential growth problem, because we see it jumps from 1 to 30.1 with just a change of positive 1 in x. And then for our second equation there, we see that it's going to be exponential decay because we go from 1 to 0.3. All right, so moving on to example 2, which is going to be number 18 in section 4.1. We have the amount of electricity in trillion kilowatt hours generated by natural gas in the United States can be approximated by the function f of x is equal to 0.10 times 1.05 to the power of x, where x corresponds to the year 1960. How many kilowatt hours were generated in the given years? So, zoom in a little bit here. If x equals 0 corresponds to the year 1960, and now our given year is 1990, so we know the year is equal to 1990. And if x equals 0 was 1960, then 1990 is going to equal x equals 30. Now all we have to do is use this equation and calculate when we plug in 30 for x. So we can say f of x is equal to So we can say, too far. We can say 0.10 times 1.05 to the power of 30, and we end up getting the value of about 0.432, and this is in terms of trillion kilowatts. So we can say trillion kilowatts. Now we can do the same thing for part B. So we know that B is the year is 2002, and we know that x equals 0 corresponds to the year 1960. So in this case, 2002, our x value is going to equal 242. And then all we have to do is plug in 42 for x. When we do this, we get 0.10 times 1.05 to the power of 42. And when we calculate this, you should get a value of about 0.776 trillion kilowatts. All right. So using the important information that we do know about section 4.1, we were able to do 2 different problems that kind of sum up a lot of the things that we learned in section 4.1. So now we can move on to section 4.2. So in section 4.2, we worked with applications of exponential functions. And then we learned the exponential growth function, or the official definition of the exponential growth function. So when we see exponential growth functions, they're always written as f of t, or you could see it as h of t, h of x, anything along those lines. This is just in general. We see f of t is equal to y naught, or the initial y value, times e to the power of k times t, where k is a constant. Or we see it written as f of t is equal to y naught, or the initial value of y, times b, the base, to the power of t. So with our first function here, the one that's highlighted in blue, we see f of t is equal to y naught times e to the power of k times t. So when k is greater than 0, we're going to have exponential growth. So when k is positive, we have exponential growth. But when k is less than 0, we have exponential decay. So that means when k is negative, we end up having exponential decay. So even though we call this the exponential growth function, by saying when certain values are equal to certain numbers, then we can say when it will be decaying and when it will be growing. So even though it's called the exponential growth function, that doesn't mean that it can't be a decaying function. So then we also have f of t is equal to y naught times b to the power of t. So when b is greater than 1, we have exponential growth. So when b is greater than 1, not just when it's positive anymore, it's when it's greater than 1, we have an exponential growth problem. Then when b is between 0 and 1, so b is still positive, now it's just between 0 and 1, we have an exponential decay equation. So it's important to remember those 2 equations, and then also kind of what makes it decay and what makes it grow. So we also learned the logistic function, which we had f of t is equal to c divided by 1 plus a times e to the power of kt, where we see that c and a and k are all going to be constants. So the logistic function is really only needed when indicated in a problem. If it's not indicated, then the chances are you don't need to use the logistic function unless it specifically says use logistic function, or function is growing logistically, or something along those lines. So unless specified that you need to use the logistic function, you don't need to use the logistic function. All right. Our first example from section 4.2 is going to be example 3 here, which is going to be number 13 in your section 4.2. So we have assembly line operations tend to have a high turnover of employees. forcing the companies involved to spend much time and effort in training new workers. It has been found that a worker who is new to the operation of a certain task on the assembly line will produce P of T items on day T, where P of T is equal to 25 minus 25 times e to the negative 0.3 t. So how many items will be produced on the first day? How many items will be produced on the 8th day? And then according to the function, what is the maximum number of items that the worker can produce? And then we want to round to the nearest whole number because you can't really produce half an item. So starting with part A here, we just want to know how many items will be produced on the first day. Since we know that T is in days, all we're asking to do here is just replace T with whatever number of day we're thinking of. So for part A, when we think about the first day, we're just replacing T with 1 and calculating P of T. So we have P of T is equal to, or first we'll define T. So we say T is equal to 1. Now we can write P of T is equal to 25 minus 25 times e to the negative 0.3 times 1. So when we calculate this value, which I highly suggest you do on your own, we end up getting a number that is around 6.4, and since we're rounding to the nearest whole number, we say this is about 6 items. So now for part B, we want to see how many items will be produced on the 8th day. So now since we're thinking about the 8th day, we're just replacing T with 8 and calculating for P of T. So for B, we can say T equals 8, and we get to do the same thing. So we say P of T is equal to 25 minus 25 times e to the negative 0.3 times 8. And this is going to give us a value of 22.73, which since we need to round to the nearest whole number, we're going to say that's about 23 items. All right, so then for part C, we want to say, according to this function, what is the maximum number of items that the worker can produce? Because we know that a worker can't produce an infinite amount of items in one day. There has to be a limit. So if we want to find that maximum number, one way we could do that is that we can use Desmos. So let's go and use Desmos to see when the maximum number will be. All right, so we have graphed our equation here. We have y is equal to 25 minus 25 times e to the power of negative 0.3 times x. So in this case, we have x and y instead of f of t and t. This is just because Desmos really likes the terms x and y. So we have this graphed here, and we see that definitely stables off around the value of 25. So we see as x increases, our value is going to stay at 25, or it's going to get really close, and then it's going to be at 25. So we can say that as x goes to infinity, then our equation will go to 25. And this will be our maximum number of items that we could produce. All right, so now we use Desmos to find our maximum number. So we said, we can say using Desmos, we got the max number of items produced in a day is 25 items. Now, using Desmos was very helpful in this case because we did get to visually see that it's going to stop increasing once we get that P of t is equal to 25. But you can't always use Desmos, or maybe we don't have a graphing calculator on hand or anything along those lines. So another way that we can do is just by checking and seeing our equation and knowing or taking the knowledge that we have about exponential functions in this case and seeing if we can apply it to this problem and seeing if we can find the answer. So we know that our equation is P of t is equal to 25 minus 25 times e to the negative 0.3t. Now what we can see here is that we have a constant minus an exponential equation. Because remember, early on we said that an exponential equation can be y naught times e to the power of kt. So we can say that this part of our equation right here is y naught e to the kt. So that is part of our equation right there. And we know that in this case that we have this version of our exponential growth function, we know that when k is less than 0, we have an exponential decay function. So our exponential decay function tells us that as x is going towards infinity, and by saying that we just mean that when x is increasing, our function is going to get closer and closer to 0, and in essence will be 0 eventually, but it will actually never be the value of 0 and it will never touch the x-axis. So if we know that this part of our equation, as the days go on, or as x goes towards infinity, or x increases, we know that this value is going to get closer and closer and closer to 0. And it's going to get closer and closer and closer to 0 very quickly. So we know that after, even after 8 days, we saw that it was going to be about 23 items. So we know pretty soon after 28 days, it's going to start hitting 25 and not being able to gain any more items per day. So using this information, we can also say, or that this part of P of t will go to 0 as x goes to infinity. What this, or t goes to infinity. There we go. So we see that as time goes on, the value that we're going to continuously keep getting is 25. And so if this value essentially is going to go to 0, we're going to get P of t is equal to 25. So we get that 25 items produced a day is the max. So we can always use Desmos or a graphing calculator. That is always a very good option to have, but we can also use logic in order to figure out where our maximum value is going to be at. All right, so moving on to our next example, example 4. We have the population of a certain town can be modeled by the function P of t is equal to P naught, or our original value of P, times 1.08 to the power of t, where t equals 0 corresponds to the year 2000. So for part A, the population in the year 2000 was 3,496, and we want to find P naught, or our original value of t. Then for part B, we're going to estimate the population in years 2007 and 2015. And we're going to round to the nearest whole number. So, starting with part A, we see here that the year 2000 is equal to t equal to 0. And we know that we want to find our P naught equation, so we're going to solve for P of t. Over here. Or we know that our population in the year 2000 was 3,496. So we'll say P of t was 3,496. Now we can set up our equation. So we say P of t, which we know is 3,496, is equal to P naught times 1.08 to the power of t, which in this case we know that t is equal to 0. So we're going to get 3,496 is equal to P naught, since we know that 1.08 to the 0 power is just going to be equal to 1. So now we have that our original value is 3,496. So this tells us that our equation is now P of t is equal to 3,496 times 1.08 to the power of t. So now for part B, we want to estimate the population in years 2007 and 2015. So what we're going to do for this is that we just want to plug in our value of t that corresponds to the year 2007 and for the year 2015. So if we consider the year 2007, and we know that t corresponds to the year 2000, that 2007 will correspond to t equaling to 7. So now we can just plug everything into our equation for P of t and solve. So we know that P of t is equal to 3,496 times 1.08, now to the power of 7. As always, I highly suggest that you calculate this value on your own. And we end up getting 5,991.5, and we need to round to the nearest whole number because you can't have a fraction of a person. So we will end up getting 5,992 people. And that would be in the year 2007. Now we want to solve for the year 2015. So we can do the exact same thing as we did before. Now the year 2015, we know that that corresponds with the value of t equaling to 15. So we calculate the same equation. So we use P of t is equal to 3,496 times 1.08 to the 15th power. I encourage you to calculate this value on your own, and you should get 11,089.9, which we round up to be 11,090 people. So, considering the fact that we started with 3,496 people, then within 7 years we had 5,992 people, and then within just 8 years after that we had 11,090 people. We know that this equation is going to end up being an exponential growth problem. And since we know the idea of population growth anyways, we know this should have ended up being an exponential growth. All right, so moving on from section 4.2, now we have section 4.3. So we learned about our common logarithms, which are just logarithms with base 10. So these are going to be the equations whenever you see An undefined log, it'll just be y equals to log of something. And there's no base there. So whenever you don't see a base or it's an undefined base, then we are always going to assume that that is log 10. And we see an example here. So in our second point, we see that there's going to be y is equal to log of x. So there's no log base 10, but we always assume that since there's no defined base, it means log base 10. Then we have that our logarithms and our exponents are related by saying that y is equal to log, in this case log base 10 of x, is the same thing as saying x is equal to 10 to the power of y. Logarithms and exponential functions are very much related in the sense that they're essentially the same thing, they're just rewritten. They're just written differently. So these are how our terms end up being arranged. So if we start with an equation that looks like this, if we start with a y is equal to log base 10 of x, or any base at all, but in this case we're going to work with base 10. So we have y is equal to log base 10 of x. So we want to rearrange this to get it in exponential form. So what we're going to do is our log, or the word log, is going to go away. So we don't write that anymore. Then our base 10 here is going to become our base when we have an exponent. So we're going to bring that to the other side of our equation. Then the original y that we had written gets raised up into an exponent. And then our x just gets to stay on that side with nothing affecting it. And this ends up becoming 10 to the power of y is equal to x. So that's how we rewrite it. This, if you wanted to go from exponential to logarithmic form, it's essentially the same thing. So instead, you would just reverse it. So your 10 would go and become the base of your logarithm. Your exponent y would just go down to being a regular number, or a regular variable, not an exponent. And then we would take that log base 10 and we would apply it to x. So we see in all of these cases that y is always our exponent, 10 is always our base, and x is our result. So that is how we write it. So when we write 10 to the y power is equal to x, that would be saying if y were 1, then y to the first power, or 10 to the first power, would be equal to 10, so x would be 10. Then if we rewrote it in our logarithmic form, it would be 1 is equal to log base 10 of 10. So your result is always what is being applied by the logarithm, and your exponent y, or your y, is always going to be your exponent. So whatever your logarithm is equal to, that is the exponent. Whatever the base is your base of your exponent, and then whatever is in the parentheses, or whatever you're taking your logarithm of, that is technically the result. So that is just how we rearrange our problems when we have logarithms and exponential functions. So we also work with natural logs, and these are just logarithms of the base e. So we remember that e was our most useful exponential value. Then we write them as y is equal to ln, so we just write ln of x. Sometimes you won't see parentheses around it, and that's okay. It's up to you whether you want to write the parentheses or not. So we see that as written as y is equal to the natural log of x. So the natural log will never have a base, because the natural log is technically y is equal to the log base of e. So the natural log already implies that you have a base e. So you don't have a base of the natural log, the base is e. Then we know that this equation, y is equal to the natural log of x, is also equal to the equation x is equal to e to the power of y. Because like we said before, we know e is the base, so e becomes our base of our exponent, which is y, equal to what we were taking the log of, which was x. So logarithms can have any base, which we refer to as a. So in the case that we had this equation here, instead of 10, we could have written a. So in that case, we know that the base could be any value, not just 10. And then if we have any other base, we can write that as y is equal to log base a of x, which is also the same thing as saying x is equal to a to the power of y. So essentially what we're doing is we're looking at the same things, we're just replacing our base. And then for natural logs, when we replace the base, we essentially are just changing what the word log looks like. So instead of writing log, we write ln. So we also learned about some properties of logarithms. So if we let x and a be any positive real numbers, so when we say that, we're talking about this equation right here. And when a is not equal to 1, and r can be any real number, then we have that the log of base a of 1 is equal to 0, and that's because if a had an exponent of 0, it would be equal to 1. Then for b, we have log base a of a is equal to 1, and that would be like saying a to the power of 1 is equal to a. Then we have log base a of a to the r power is equal to r. Since we know that r is our exponent and a is our base, we know that a to the power of r would be equal to a to the power of r. Then we have that a raised to the power of log base a of x is equal to x. So this is essentially like saying your a as a base of an exponent cancels out if your exponent is the log of the same base. All right, so that is also just like saying if you want to rearrange it in terms of logarithms, you would essentially have log base a of x is equal to log base a of x when you rearranged it. And you know that that's true because they would equal each other. Then we have the product, quotient, and power properties. So we let x, y, and a be any positive real numbers with a still not equaling to 1. We let r be any real number. Then we have log base a of x times y is equal to log base a of x plus log base a of y. So this is the product property. So it allows us to take terms that are being multiplied and separate them into two separate terms where they're being added together. Then we can do the same thing for a quotient. So we can say that log base a of x divided by y is the same thing as saying log base a of x minus log base a of y. Then we have lastly our power properties. We have log base a of x to the power of r is equal to r times log base a of x. So whenever you have an exponent inside the parentheses of a logarithm, you can just take the exponent and bring it out to the front to have it multiplied by your equation instead. All of these terms that we just had, they work both ways. So if you have log base a of x plus log base a of y, you can turn that also into log base a of x times y. Same thing goes for log base a of x minus log base a of y. You can turn that into log base a of x divided by y. And if you have r times log base a of x, you can turn that into log base a of x to the r power. So these properties that we see, they work both ways. Just make sure that that is what you have, because you cannot separate something that looks like log base a of x plus y. That doesn't separate into anything. That is its own entity. It is not the same as having log base a of x plus log base a of y. Remember, we made a caution note about that in our section 4.3 notes. So if you ever need to look at that again, that's where you should go to look at those cautionary notes. So now we can also calculate logarithms with base a using our change of base theorem. And we really like to use this theorem because unless you have specific types of calculators, you can't always just define a base of a logarithm, because if you just type logarithm into your calculator, it automatically assumes log base 10. If you put in natural log or ln of something into your calculator, it's going to automatically assume base e or log base e. So if you ever have a value that's not 10 or e, then you can use your change of base theorem, and this allows us to take log base a of x and make it equal to the natural log of x divided by the natural log of a. And this is going to end up being very useful when we have to calculate logs with different bases in equations. Then we have that the graphs of logarithmic functions and exponential functions appear mirrored or opposite. So by looking at our definition here, first we see exponential functions, we see a graph that looks like an exponential growth function, and we have f of x is equal to a times x. The domain is a set of all real numbers, and the range is the set of all positive real numbers. So remember, domain means x and range means y. Then we have that our horizontal asymptote, and there's no vertical asymptote. Then if we look at our logarithmic function, we see f of x is equal to log base a of x, so we're assuming base a. And we're saying that the domain is the set of all positive real numbers. So our x values will always be positive, never 0. And our range is a set of all real numbers. And we have a vertical asymptote and no horizontal asymptote. So we see here that if we graph them on the same graph, that they would look mirrored or opposite. We would say we have one graph going this way and one graph going this way. And we also did that in section 4.3 as well. All right. Moving on to our example, we have example 5. So we say the population growth of frogs is described by the equation f of t is equal to 732 plus 61 times log base 4 of 3t minus 1, where t is measured in months. We want to find the population of frogs after 4.5 years, and we want to round this to the nearest whole number. Okay, so we have our equation here, and what we want to do is find our population of frogs after 4.5 years. We know that t is measured in months, so we need to convert 4.5 years into terms of t, or months. So we take 4.5, multiply that by 12, and we end up getting 54 months. So we get that t is going to be equal to 54. So since we found the value of t, we can plug in everything to our equation and try to solve for f of t. This ends up giving us f of t is equal to 732 plus 61 times log base 4 of 3 times 54 minus 1. Then we want to just simplify this equation. We get f of t is equal to 732 plus 61 times log base 4, and you should end up getting 161. So now we have a logarithm with base 4 of 161. Now, it's hard to find a calculator that will calculate this value, especially with a different base. So we're going to use our change of base. So let's highlight it. And we're going to say, let's use our change of base theorem. So, and if we're going to use it, let's write it over here. So we know that log base 4 of 161. Using our change of base theorem, let's actually pull this down just a little bit. Using our change of base theorem, which we defined earlier here, we know that log base a of x is equal to the natural log of x divided by the natural log of a. So in this case, we see that 4 is a and 161 is x. So we can rewrite this and say the natural log of 161 divided by the natural log of 4. Highly suggest that you calculate this value on your own, and you should end up getting 3.665. And since we're not done with our calculations, let's leave it to 3 decimal places so we can get a more accurate value. Okay, so we found our value of the log base 4 of 161 using our change of base theorem, and now we're going to take this value and we're going to plug it into f of t. So we know that f of t is equal to 732 plus 61 times 3.665. I see that we use this value and we plugged it in for our logarithm. Now all we have to do is calculate it. So if you calculate this on your own and we want to round to the nearest whole number, you should end up getting 955.6, which we're going to say is about 956 frogs. So that is how we ended up being able to round to the nearest whole number using our change of base theorem when we have a different base as our logarithm. All right, so now we can do example 6. So what we're going to do here is we're going to write the expressions as a sum or difference of logarithms with all variables to the first degree. So this is saying that we want to take this equation that has multiplication, it has an exponent, and we're going to write it out. So that is a sum, so we're going to have terms adding up or terms being subtracted from one another. And then we don't want any exponents. We want them all to be worked out using our properties. So just another quick look at our properties here that are going to be really important, our product, quotient, and power properties. So taking a look at that, now we can use them. So for part A here, it's best to work out to n. So in this case, we have the natural log of the third root, or this is essentially going to be an exponent of 1/3 of 7 times u to the 6th power times v to the 9th power. So first things first, we really want to rewrite that third root. We want to rewrite it as an exponent of 1/3. So we can say this can become the natural log of 7 times u to the 6th power times v to the 9th power, and this is to the power of 1/3. So now we see something that's very obvious. We have an exponent in our natural log, so we can use our power rule. So we'll use this again, and we'll use our power rule to say 1/3 times the natural log of 7u to the 6th power times v to the 9th power. So now we see we have two terms being multiplied by each other. They both have exponents, but these exponents are not being applied evenly. So we'll need to separate them before we can separate their exponents. So in order to do this, we know we still have our 1/3, so we're going to put that outside of our brackets. So we're going to separate these terms. Let's start by doing the natural log of 7u to the 6th power. So we'll say natural log of 7 times u to the 6th power. And then we'll say plus the natural log of v to the 9th power. Then we can simplify this further so we can pull out our exponents now. So we can pull our exponent out of our second term for sure, but what we notice here in our first term is that we have a natural log of 7 times u to the 6th power. Now, the exponent of 6 is only being applied to u, so what we're seeing here is that we have two separate things being multiplied. So now we'll need to separate our natural log of 7 and our natural log of u to the 6th power. So this ends up giving us the natural log of 7 plus the natural log of u to the 6th power. Now, v to the 9th power is the only thing we have to worry about, so let's take out that exponent. And when we do that, we get 9 times the natural log of v. Now all that's left is we take out our exponent and the natural log of u to the 6th power. What we end up getting is the natural log of 7 plus the natural log, 6 times the natural log of u plus 9 times the natural log of v. And I just barely ran out of room. Just barely, so let me move over part B here. And what we end up getting is our final answer, because we want to simplify this term, we're going to distribute our 1/3, and we end up getting 1/3 times the natural log of 7 plus 2 times, let's move this down so it's not running into part B here. So let's pull it down to right here, replace our arrow. Then we have 2 times the natural log of u, and as to not run into all the room of b, we'll add our next term here, which is going to be 3 times the natural log of v. So we see here that this is going to be our equation. And actually, sorry, I'm moving this around so much. We'll just put it down here so that it's all in one line and we can move our value of b back, or move our problem b back. So it becomes that. Okay, hopefully we don't have the same issue here with part B. We'll just scooch it back just a little. All right, so we see that when we ended up simplifying, we end up simplifying to 1/3 times the natural log of 7 plus 2 times the natural log of u plus 3 times the natural log of v. There are other ways that you can do this, of course. You can do things in different orders. We could have applied the cube root from the very beginning and just not have dealt with that exponent. But either way, you should end up with the same answer, which is 1/3 times the natural log of 7 plus 2 times the natural log of u plus 3 times the natural log of v. So now we can move on to part B. So in this case, we have a value divided by another value. So the first thing we want to do is use our quotient rule. So by first using our quotient rule, we end up simplifying this to the natural log of 3z to the 4th minus the natural log of the square root of h times z. We see that technically both of these terms have exponents, since we know that we can rewrite our square root as the power of 1/2. So let's do that first. So we'll keep the natural log of 3 times z to the 4th power. And then this becomes minus the natural log of h times z to the 1/2. So now we can replace our exponents. And we see that this is going to become 4 times the natural log of 3z minus 1/2 times the natural log of hz. Looks great, aside from the fact that we have two values that are being multiplied inside each of our natural logs. So now we need to use our product rule to separate each one of our natural logs. this is going to end up becoming 4 times the natural log of 3 plus the natural log of z. That's a z, not a 2. All right, I'll draw the little line in between so we know. Well, there's a lot of z's in this problem. There we go. Okay. So now we can go into our second part, which we have is minus 1/2 times the natural log of h plus the natural log of z. And now we want to simplify, so we're going to distribute our values that were being multiplied, and then we'll simplify. So first we distribute, so we get 4 times the natural log of 3 plus 4 times the natural log of z, and then we have minus 1/2 times the natural log of h minus, because remember this negative or this subtraction sign is applying to both terms in our brackets here. So we have minus 1/2 times the natural log of z. Now we're almost there. The only thing left that we see is that we have 2 natural logs of z. So we can simplify these values. So let's bring this up here. And we say that this is going to be equal to 4 times the natural log of 3. Let's leave our z for last, so we'll say minus 1/2 times the natural log of h. And then we have 4 times the natural log of z minus 1/2 times the natural log of z. So what we're doing is we're saying 4 natural log of z minus 1/2 natural log of z. We know that 4 is equal to 8 divided by 2. So when we subtract 1 divided by 2, we end up getting 7 divided by 2 times the natural log of z. And that is how we end up being able to simplify an equation that looks like this into an equation that looks like this. So we see we have completed because we have expressions as sums or differences, and all variables are to the first degree. So we see that using our properties of logarithms can be extremely useful in many cases, including this, to simplify down our equations even more so that it becomes more manageable parts. All right, and then for example 7 here, all we're going to do is convert between logarithmic and exponential notation. So we're just rewriting everything. So we remember that 7 is going to be, or in this case for part A, we have 343. I got too far ahead of myself. We have A, which is 343 to the power of 1/3 is equal to 7. So we know that 7 is our exponent, 343 is our base. I'm sorry, 7 is our result. I was very much had the thought of a logarithmic problem stuck in my head, so I apologize for that. 343 is our base, 1/3 is our exponent, and 7 is our result. So we want to take our problem here, which is written as exponential form, and we're rewriting it into logarithmic form. We know that when we have our logarithmic form, we have the log of base A of x is equal to y, y being our exponent, x being our result, and a being our base. So when we rewrite this, we know this will be written as log of our base, which was 343, of our result, which is of 7, equal to our exponent, which is 1/3. So that's just how we would rewrite something that is in exponential form. We rewrite it to be in logarithmic form. And this is with using different bases and a little bit more complicated considering that we had a base that was in the hundreds and our results was just 7. Now let's do it the other way. So for part B, we have log base 11 of 1 divided by 14,641 is equal to negative 4. So we remember that 4 here we know is going to be our exponent. 11 is our base. And this value here is our result, or value of x. So you know that's our base. We know this is x and our exponent y. So now to rewrite this in exponential form, we know we start with our base, which is 11, to our exponent, which is negative 4, equal to x, which is our result, or 1 divided by 14,641. So that's how we rewrite our logarithmic and exponential equations to have the opposite notation. All right, in our last section, section 4.4, we just learned some more properties of logarithms and exponential functions that are very helpful when solving for problems. So starting off, we have a, or let a be a positive real number not equal to 1. Then if a to the power of u is equal to a to the power of v, then we see that u is equal to v. Then we have let u, v, and a be positive real numbers with a not equal to 1. Then if we have log base a of u is equal to log base a of v, then u is equal to v. Lastly, if a and u are positive real numbers with a not equal to 1, then we have that a raised to the power of log of a of log base a of u, that's just going to be equal to u. So this very last property that we have, we actually learned that back in section 4.3. They just replaced u with the value of r. But as for the first two properties, we see that these are going to be extremely useful. And because we know that these are very useful properties, we want to manipulate our equations so that they look something like this so that we can use these properties. So basically just a reiteration, we see that these properties help us solve equations involving logarithmic and exponential equations. So they're very helpful when trying to solve for equations. So for example A, all we're going to do is solve the logarithmic and exponential equations. Specifically, we really want to use our properties, and they're going to be very helpful in this case. So for part A, we have the natural log of 10x minus 1 is equal to 2 times the natural log of 7. So when we rewrite this, we know that whenever we have log with the same base of anything, we know that u is equal to v. But what we don't really know is why there's a 2 in front of our second logarithm. That doesn't really match our definition or our property, so we're going to need to manipulate it a little bit so that it matches our property exactly. We know that it is the natural log of both sides, so we know that's log base e, of course. But let's rewrite our second part here. We're going to use our power property, and we're going to take our 2 and we're going to put it back into the exponent. So when we rewrite it, we get the natural log of 10x minus 1, that doesn't change. And we're putting our 2 back inside of our logarithm. So we get log, the natural log, 7 squared. And now we want to solve. So now we have the natural log of 10x minus 1 is equal to the natural log of 49, because that's 7 squared. So now we have the natural log of a term equal to the natural log of another term. Or in other words, we have the natural log of u is equal to the natural log of v, so we can just set u equal to v. So all we have to do is set 10x minus 1 equal to 49. And that's about it. Now we just have to solve for x. because now we used our property to completely get rid of our logarithms, and all we're dealing with is whatever was inside our parentheses. Now we can add 1 to both sides. We end up getting 10x is equal to 50. We divide by 10, and we see that x is equal to 5. So we solved for x. And if we think about it, we see here, if we plug it back into our original equation, we know that the natural log of 10 times 5 is 50 minus 1, so we'll get the natural log of 49. Once we put that 2 back in the exponent for our second logarithm, we know that'll be the logarithm of 49. So we know that this is correct by checking that. Now we have part B. So we have 3 to the power of 1/2 x plus 3 is equal to 27 to the power of 2x plus 7. Now, going back to look at our property, we know that if a to the power of u is equal to a to the power of v, then u is equal to v. But we see here we don't have the same base. But what we do have is that 27 is a multiple of 3, or in other words, 27 is also essentially going to be an exponent of 3, or it's the result of 3 with a certain exponent. And if we think about it, 3 to the power of 3 is equal to 27. So let's rewrite 27 as 3 to the power of 3. When we rewrite this, we'll keep our first term the same. So we still have 3 to the 1/2 x plus 3. But now we have 3 to the 3rd power to the power of 2x plus 7. And now we know that we have a base with an exponent raised to another exponent. When we have that, what we can do is just multiply our exponents. This ends up giving us 3 to the 1/2 power of x plus 3 is equal to 3 to the power of 3 times 2x plus 7. Now let's distribute that 3 so we can use our property. Or we can use our property right now, actually. So let's just do that. We have the same base, and we essentially have our u, and we have our v. So we can use our property to state that 1/2 x plus 3, that x is not in the denominator, it's just being multiplied, is equal to 3 times 2x plus 7. Now we just solve for x. So first thing we really want to do is just distribute the 3. We end up getting 6x plus 21. And now we can subtract 3. This gives us 1/2 x is equal to 6x plus 18. And we're about to run into another problem, so let's pull this up here. So we have 1/2 x is equal to 6x plus 18. And we want to subtract our 6x. We know that 6x is essentially like saying 12 divided by 2. So when we have 1 minus 6, it's technically 1/2 divided by 11 divided by 2. So when we do that, 12 divided by 2, we end up getting 11 divided by 2. X. And we know that's equal to 18. Then we can multiply each side by 2. We get 11x is equal to 36. Then we want to divide by 11, and we get x is equal to 36 divided by 11. So we see that using these properties really come in handy when solving these equations, because it allows us to just immediately get rid of our base or our logarithm. And then we don't have to deal with the extra steps of actually getting rid of them. All right, for our last problem, for example 9 here, we have, this is number 78 in your book, if you want to go look at it, in section 4.4. So we have the revenue in billions of dollars for Walt Disney Company can be approximated by the function r of x is equal to 16.2 plus 9.992 times the natural log of x, where x equals 3 corresponds to the year 2003. This also basically tells us that x equals 0 corresponds to the year 2000. They like to write that as a way to kind of mess with you. But we also know x equals 0 corresponds to the year 2000. So remembering this. We want to find each of the following. So we want to find R of 9, which essentially this means 2009. Then we want to find R of 12, which is essentially 2012. And then for part C, we say if the model remains accurate, in what year will the revenue reach 50 billion? Starting with part A, we want to find R of 9. Okay. Which we know this is going to be our revenue in 2009. So now all we want to do is plug in 9 for x. So we know that our revenue equation is 16.20 plus 9.992 times the natural log of 9. Then we can just plug this straight into a calculator, which I highly suggest that you do on your own. And you should end up getting about 38.15, and this is in billions. Billions, yeah. And it's in dollars, so $38.15 billion. Now for part B, we want to calculate the revenue from the year 2012. So we have R of 12, which we know is the revenue in 2012. And we get to do the same thing. So we say R of 12 is equal to 16.20 plus 9.992 times the natural log of 12. Then when we calculate R of 12, you just plug this into a calculator, which, as always, I highly recommend that you do. You end up getting $41.03 billion. Now for part C, we say if the model remains accurate, in what year is revenue going to reach 50 billion? So we know our revenue is our estimate of R of X, but we want to find what year the revenue will reach 50 billion. So what we're going to do is we're going to plug in 50 for R of X, and we're going to solve for X. So we say 50 billion is equal to R of X, and we want to solve the year. So we have 50. We know this is already in terms of billions, so we don't have to, write out all the zeros that come along with that. We know this is going to be 50 equal to 16.20 plus 9.992 times the natural log of X. So first things first, we just want to simplify down to X. So let's subtract 16.20. This gives us 33.8 is equal to 9.992 of the natural log of X. Now we just want to divide by 9.992 in order to get rid of it. So I say 9.992. And this gives us 3.3827 is equal to the natural log of X. I'm going to pull this up here so it doesn't get too long so we can view everything at the same time. 7. So what we can do in order to simplify for X is we are essentially going to raise each side of our function here as an exponent of e, because this is going to give us e to the 3.3827 power is equal to e to the natural log of X. Now we know that the natural log of X is like saying the natural log of the base e, so this is like saying e to the natural log, or the log base e of X, which we can go up to our properties, And we see our last property here tells us a to the power of log base a of u is just equal to u. So we know that since the natural log is log base e, this is going to be equal to x from using our property. Now, since we know that this is equal to x, we get that x is equal to e to the power of 3.3827. So if we calculate that on our own, we end up getting 29.45, which tells us that revenue will reach 50 billion in the year 2029 if everything stays the same. All right, zoom out. Come on, a little more. There we go. All right, so that concludes our review of chapter 4. So don't forget that your test is tomorrow. You also have to take your quiz today, so I would highly suggest, if you have not yet, I would suggest that you do this first and then take your quiz, and then tomorrow you can take your exam. As always, if you have any questions or concerns at all, please feel free to send me an email, or you can come into my office hours or anything along those lines. Okay, so I will see you all virtually later, and good luck on your test.